Hello, I'm Dave Finley, Public Information Officer for the National Radio Astronomy Observatory. I'm here at the American Astronomical Society meeting in Washington, D.C. with one of our astronomers at NRAO, Dr. Scott Ransom. Scott's pretty excited about some new discoveries he's announced here.
That's right, yeah, Dave. So during this meeting, we're announcing the discovery of 17 new millisecond pulsars. Now, millisecond pulsars are spinning hundreds of times per second, and they can be used for a lot of basic physics tests, including potentially the direct detection of gravitational waves. And the problem is that they're normally really, really hard to find. They take huge amounts of telescope time, radio telescope time, CPU centuries of computing, and tons of man hours in order to find them in normal surveys, but we found them in only a few short months using one of NASA's new satellites called the Fermi Observatory.
And how did the Fermi Observatory help you do this?
Well, so what's happens is the Fermi Observatory observes gamma rays, and it's an all-sky gamma ray instrument, and so it collects gamma rays constantly. It's constantly scanning the whole sky, and over the last about 14 or 15 months, it's been accumulating a very, very deep gamma ray image of the whole sky. And in that gamma ray image are a bunch of point sources that are gamma ray sources, many of which we know what they are. They're blazars, active galaxies, or even some known pulsars in our galaxy. Those are the two main types of gamma ray sources, blazars and pulsars. But most of those pulsars that have been found have been young pulsars. But what's happened recently is that Fermi has showed that several radio millisecond pulsars actually emit gamma rays. And so once that was confirmed that millisecond pulsars have gamma rays, then we decided to make a collaboration, a consortium of international radio astronomers using the biggest radio telescopes in the world. This was also spearheaded by Paul Ray at the Naval Research Lab. And then we're using these radio telescopes to go after these unassociated point sources. So if there's a Fermi source in the sky that doesn't have a known blazar or pulsar, we look at it with these big radio telescopes. And this has caused a bonanza of new discoveries. So basically what's happening is Fermi's provided us a treasure map of where to look for these very valuable millisecond pulsars. So we don't have to search over the whole sky, but we have a pinpoint spot on the sky then that we can find these objects.
And where exactly in the universe are you finding these? Are they in our own galaxy, or are they external galaxies? Where are they?
Yeah, so all pulsars that we know of are basically in our own galaxy. And so these millisecond pulsars are in fact very, very close to us. They're galactic neighbors. They're only a few hundreds, maybe even a couple thousand light years away, which is very, very close by on the galactic scale. And they're spread out over the whole sky. Most young pulsars, which have been the traditional gamma ray sources, have been in the plane of the galaxy. But these millisecond pulsars, because they're very, very nearby, are scattered all over the whole sky. And that's actually an important thing for gravitational wave detection experiments.
Okay, and that's gravitational waves. Tell us what gravitational waves are and how you connect them with pulsars. What's the connection here?
Right, so gravitational waves are ripples in space-time, and they're caused by any type of moving massive object. Well, in the centers of very distant galaxies, you can often have binary black holes. So two black holes, two supermassive black holes that are orbiting one another. And when they orbit each other on years timescales, they cause ripples through space-time that travel throughout the whole universe. Well, they're passing over us in the Earth right now. And the neat thing what we can do, there's an international effort to use millisecond pulsars, just like the kind that we're finding now, to use an array of those, many of them, 20 or 30, and measure the timing very, very precisely. So we measure when the pulses arrive at Earth. And if a gravitational wave is passing between us and the pulsar, it causes that timing to jitter a little bit. It causes it to either be delayed or come early. And so if we look at all these pulsars together, we can see a pattern in these delays or arrival times coming early. And that pattern there's a very distinctive pattern for gravitational waves. And if we find that would be the first direct detection of gravitational waves. And this is the same exact type of gravitational waves, but at a much lower frequency that they're trying to find with the LIGO observatories, with the big interferometers on the ground.
Now, gravitational waves were predicted almost 100 years ago by Albert Einstein, and still no direct detection. So you're really looking here at a new technique of confirming one of Einstein's predictions.
That's right. So it's a new technique. There's several possible ways of detecting gravitational waves, but no one has done it directly yet. There's been an indirect detection by using another binary pulsar system. But the cool thing would be to make a direct detection. And one of the problems that we've had so far with doing it with pulsars is that there simply aren't enough very good, bright millisecond pulsars. And so this is where Fermi comes in. A lot of these new sources we're finding are very bright radio millisecond pulsars, and that's exactly the kind we need for gravitational wave detection. So Fermi, this NASA mission that no one had ever thought would help this big radio project to detect gravitational waves, is now providing a very key bit of input into it.
And it also, I think you said, it's important that they're spread out all across the sky. It helps make your detector array wider, if you will.
That's right. Yeah, so because the gravitational waves are coming from these very distant galaxies, they could be anywhere with respect to the Earth in the sky. So if we have an ensemble of them in every direction, it helps create like a uniform coverage in our sensitivity for gravitational waves, because these gravitational waves are going to be coming from basically everywhere.
And you've got 17 new ones, but you also have a lot more point sources on that treasure map. Is that correct?
Right. Yeah, so as Fermi keeps observing and observing, its map of the sources in the sky keeps getting deeper and deeper, and more sources pop up. And so, but over the next couple of years, there's going to be hundreds of sources that we need to search. We've got supercomputers working on them right now, and a lot of telescope time from the big radio observatories is being used. And so we really think it's quite likely that we're going to find a lot of new millisecond pulsars. And I should just make one other point, is that to see how much of an increase in millisecond pulsars, we only know of about 60 millisecond pulsars in our galaxy, and that's taken us 30 years to discover them. But we found these latest 17 in only the last 3 months. So it's a huge new improvement and a very new and exciting way of finding these things.
And I take it that the more millisecond pulsars you have and that you can time precisely, the better chances you have of quickly detecting gravitational waves.
Yes, that's right. The significance of a detection for gravitational waves is completely directly proportional to the number of pulsars that we have that we're using. So if we have twice as many pulsars, our detection will be twice as strong in gravitational waves. So that's a very important thing for us, since the gravitational waves are incredibly weak, and it'll be very difficult to detect, but this is going to help us a lot.
Well, very good. And that's basic fundamental physics coming out of a cooperation between gamma ray and radio astronomy, but millisecond pulsars also can be used as laboratories for other kinds of physics. Is that correct?
That's correct. Yeah, so one of the things that we'll also be able to do with these pulsars, some of them, almost all of them are in binaries. Some of them have eclipses that can teach you things about plasma physics. We don't understand what causes these eclipses. It tells you things about binaries and stellar evolution. Other of these systems have a pulsar around a very nice white dwarf, and they're general relativistic laboratories, so we can measure the masses of the neutron stars. That lets us test nuclear physics. So there's a whole wide variety of basic physics that can come out of these objects, and we're hoping that that's going to come with all these new Fermi millisecond pulsars.
So once again, we have the very large things out there in the universe, and radio telescopes and other types of telescopes, all providing us a really nice natural physics lab that we really couldn't reproduce here on Earth.
Oh, that's completely true. Yeah, these are tremendously exotic objects, the pulsars themselves, and then being able to use them as tools to study these other exotic phenomena is really amazing, and you can only do that with astrophysics.
Well, thank you very much, Scott, and we're just as excited as you are about these new discoveries, and we look forward to seeing what comes in the next couple of years or so. And thank you for watching. I'm Dave Finley from the National Radio Astronomy Observatory.